welcome to my channel Mechanical Buzz. So last video we tried to explain the principle of a four-stroke petrol engine, and coming videos that gonna upload it here in this channel, we will talk on SI engine for a long time, because we need to understand the theory very important, very precisely. So before watching this video, I would like to request the audience and our viewers, please do some basic research, at least have a basic knowledge on engine. You can have another YouTube channel where the basics are explained there, or you can see the first video also, but you need a basic knowledge to understand this theory. So let's go on. So last day I talked about how engine works and what actually engine does. Engine is what is a converter. What it converts, actually, it converts the chemical energy, the form of chemical energy, to mechanical energy, because you're not gonna dating with the engine, because you're gonna use the engine to run the vehicle, right? So to run the vehicle, to move the vehicle, you need mechanical energy. That's what you get from chemical combustion inside the cylinder. Yes, the chemical combustion. So we talked about the combustion last video, because it is the main factor and it is the main objective of any engine. Yeah, that's correct. It is the main objective and it's the main purpose to design an engine, creating a combustion, and that combustion will create a huge torque on piston, and then and on and on. So we talked about first ignition, then combustion, and then an explosion. So we try to understand that through a matches. This is a match, and if I ignite it, it's gonna burn. So before it is burning, or it have some flames, before it's totally burned, it got some flames here, or it got a little spark by creating a frictions or rubbing here in this side, in the firecrackers here. So by this thing, the first what happened, that this firecracker has been ignited, okay, and then it is totally burnt right now. I mean, this portion. So this is called the combustion process. So combustion is anything that burns. Anything that burns is called combustion. But a very important theory behind of combustion is that if you want to have a combustion, you need three things that I boxed over here. I logged them boxed over here, the three factors which is very important to make a combustion. So the first one is combustible mixture. Actually, if you say it's a mixture, that is for engine, but it is that you need some combustible matter. Like this one, it is combustible, it can burn. Anything that can burn is a combustible matter. So, and if you take as an example, water is not combustible because it's got hydrogen and oxygen, but this one got hydrogen and carbon, so that is called a hydrocarbon. That anything that have hydrocarbon is combustible. So the first thing is that the combustible mixture, okay, and the second thing is the initiator or igniter. So this is very important here, as it is portrayed in your video screen. We talked about spark plug last night, because the combustion that is needed to happen before pot stroke, or in pot stroke, that you need a spark, and the spark is coming out of spark plug, and that spark plug is called igniter. And to burn it properly, you need igniter here, and the igniter is this one. You rub here, and ignition occurs here, and you have igniter here. So the second thing is that you need igniter, and the third thing is very important. That's what I'm gonna explain here with this diagram. Okay, if you look very carefully. The third one is what I've written, is that stabilization or self-propagation in combustion chamber. What does mean that? Stabilization, stable, right? Okay, I'm in a stable position, right? My hand is stable positions. or if you are riding in a car, you are going to a stable movement, okay? Or if you have any chance to, fly by airplane, then you can actually feel that the airplane keeps itself stable in the air, and that's how actually stability I can portray on your visualization. So exactly, that's how stabilization occurs here also. When you burn here, that the flames goes from the tip of the nucleus flame, that the flame started to burn this thing, has a stable movement through the combustible matter. That's how, if I explain you again, if I ignite it again, okay, you see that? The fire will come up here after, if it's if it's got a chance, or if it got a proper environment, it will burn here also. So the burning pattern is a stabilization movement there, okay, burning from here to here, here to here. The flame will come and come and come and come, and with a stable movement and the velocity, the flame will come, right? It's like that inside the cylinder of a engine, because as combustion occurs inside a cylinder, the stabilization or self-propagation of a flame is very important. That's what we can look very precisely without a magnifying glass, right? This is not a joke. So we need to understand, the first thing is that ignition limit is what. So what is the ignition limit here? Okay, take another example. Thanks to these matches, it's helping a lot. If it's got weight, it can't burn, right? Because it is not in a position, or it is not in a situation to burn it, because it's got weight. To burn it, you need to create an environment, or you need to create your surroundings positive to burning it, right? Okay, so ignition limit is what? If it's quite a dry and some of moisture comes up here, it will still burn, because um, the soaking of water is not so strong that cannot create any spark here. But if you slowly increase the amount of humidity, or I'm sorry, of moisture here, and once a time you get it very much weighted, then you can't actually burn it. So that is called ignition limit. So there are some limitations that ignition can occur. So inside the cylinder of an engine, there is an ignition scale. So before understanding about the ignition limit, we need to understand the idea of air-fuel mixture, as because the fuel and the oxygen, as we have discussed last night, is that the fuel contain hydrocarbon and the air contain oxygen. That's what the result is: carbon dioxide and H2O, water. It's a complete combustion chemical reaction. There are a lot of things can comes out. I'm not mentioning it, but it's a very simple one. So what happens actually? Uh, so to burn it, you need a hydrocarbon that you can get from petrol, and the oxygen that can hear. So the fuel and the air have a mixture between, as I have said, that combustible mixture for engine, right? So there is a ratio that maintains how much portion of air is going to take place in the mixture, and how much for fuel. So the stoichiometric ratio, which is very appropriate, think is a very appropriate, and you have already, actually, if you have a basic knowledge on that, you have already heard that what is stoichiometric ratio, air-fuel ratio here. So the air-fuel ratio is the stoichiometric for SI engines over petrol is 1:15 or 1:14.5. Okay, so ignition limit is what is dependent on that ratio, because if your engine is getting 1:14.5 or 1:15, the air-fuel ratio, your engine gonna burn very smoothly. If other factors like cylinder and everything is okay, then the air-fuel ratio is also okay, and the fuel quality is very good, then your engine is gonna smile on you. But If you decrease it very or increase the ratio, then your engine is not gonna smile on you, rather than it's got angry on you. Okay, so whatever. So the limitation is gonna measure, or to calibrating that, you need this air fuel ratio. As you can see here, this scale here I try to draw is, I have drawn here these less dense lines over here, diagonal lines on this area, 7 to 9. 7 means what? 1:7 here, and above it, this is lesser. And about 7 or before 7 is pointing out that it can be 1:6, 1:5, anything, but that is before 7. The number is before 7. And from 7 to 30, you can see that actually the ignition cannot occur. Yes. From 7 to 30, ignition can take place. But not necessarily it's sufficient. And either to reach a lean, sometimes it can take places. I mean, the ignition can happen through the spark plug. Okay, it will come up ignition, but spark plug will ignite. But I'm talking about the combustible mixture actually. You can ignite the spark plug, but you can't ignite the air fuel mixture or the combustible mixture, that called the air fuel ratio, if your air fuel ratio is out of this scale. So your air fuel ratio has to be between 7 to 30. Okay, so out of it, your engine not gonna fire. And the practical limit is what? This is a theoretical limit here. Okay, but the practical limit is that your engine must need 1:9 to 1:21 between this. But the best one is 1:14.5. That is what the stoichiometric ratio. So this what is the ignition limit. Out of it, you can, out of 30 is too lean. There practically, if there is 1% of fuel there and 30% of air, so there is no, it doesn't make sense to burn and make explosion with that thing. Okay, and here it is, if too rich, so it also can't burn, because that flame is not enough to burn it. And that is not important, because here you have less amount of oxygen to burn it. Actually, without oxygen you can't burn it, whatever the combustion mixture is. But you always need your wife here, because of, to combustible mixture, oxygen is kind of like a wife. Okay, whatever. Proceeding to this diagram over here. So I hope that you understand this ignition limit here, that you got some limit that can can make you limited of your ignition, for your ignition. So we will go further on that thing. So now Mr. Ricardo, or Richard, yeah, his name is Richard, I'm sorry, Mr. Richard. He's the father of engine research. He's been known as the father of engine research. He had said that the engine and the combustion take place is based on his theory, is that either a nucleus flames that propagate, or the self-propagation from the nucleus flame took place the full combustion chamber, or the spray of the flame causes the combustion chamber. Okay, whatever. But the important thing is that Mr. Richard has said us that the combustion, the total combustion from ignition to the burning gases, there are 3 stages there. I'm gonna write up here. I'm gonna write that. The first one is ignition leg. Second one is what do you call that? Self-propagation. I'm sorry that it's not getting enough space, so I'm writing here self-propagation. Okay, self-propagation, you can write here. Okay, boxing it up, that's been, I isolated it. And the third one is afterburning. Okay, after burning it. Okay, so we're gonna look out this 3 stages of combustion. Before that, we have to understand the theory of the combustion. Okay, so to do so, I draw here two schematic diagrams of two stages of engine, four-stroke engine, one compression and the second one is power. So understanding for the basic combustion theory is that if any combustion is happening, you need to look at very carefully. Okay, so what I'm actually talking about, please, attentively try to understand. So you have to put attention in this diagram because we are not gonna we will come to explain it later after it. So from 0 to 360 degree here is mean that if a crankshaft over here, as you can see that the crankshaft is rotating fully, that means that 0 to 360 degree, that's what the basic geometry sense actually. The circle actually have 360 degree, right? So if the crankshaft is rotating once, then it has rotated for 360 degree, and if it is completing two circle, so that means that 360 degree twice times 2 means 720 degree here. So in four-stroke engine, we got power in the interval of 720 degree. Okay, in every 720 degree, there one power and one boom or one combustion and one explosion gonna happen. Okay, so whatever. Now, to 0 to 3. Okay, the one thing is that what we have discussed last video is that a stroke happen from if the piston travels from TDC to BDC, either BDC to TDC, and if it's complete one stroke, that's meaning it has completed 180 degree. Remember, 180 degree. So if you divide 180 degrees, so that sense is 4. That's means 4 stroke happen. If the one stroke is covering 180 degree, then 720 degree covers 4 stroke there. So one stroke means 180 degree. So you can see here the point is denoting the TDC, the top dead center. In this straight line, this is the movement of piston, okay? And in this line, or in vertical line, it's denoted in this XY diagram, the pressure. So if your point is going in straight line, horizontally, that means your engine is running and your piston is moving up and down. So starting from here is that from 0 degree, the piston, if in compression stroke, in 0 degree means that the compression stroke has been started, okay, from BDC, and the piston is going up and up and up, and the piston is going up, and the crank angle is increasing as because the crank angle is increasing, that means from 0 to it's going towards 180 degree, and simultaneously it is compressing something, right? The combustible mixture inside of it is compressing, and that's why the pressure is increasing. As we discussed last video, is that if anything is compressed, then volume decreases and pressure increases. Okay, that's the pressure law of Boyle's, Mr. Boyle's, thanks to him. So we can see in this diagram that the piston is moving up and the crank angle is increasing, the crankshaft is rotating, and the piston is compressing, something that can burn, and the compression stroke is happening here. And from A to B, we can say that the compression stroke from BDC to TDC here, you can write here BDC, or I haven't write here BDC because compression stroke doesn't start from BDC actually. So from BDC, this is a theoretical, so that's why I have to write it here. So from BDC to TDC here, you can say that A to B is called a compression stroke. And from this point, you see that the piston is not moving. That means the volume here is remain constant, right? If it's stuck here, that means the constant volume is taking place. Remember that this diagram is the theoretical one. It's not the practical thing, okay? So don't get puzzled. And from B to C here, the pressure is increasing in a constant volume here. The pressure is increasing. And after that, it's mean that the combustion takes place in expansion. That means the power stroke here. from here the power stroke occurs after the ignition. There's explosion happens and piston goes down from TSU to BDC, and that's what the expansion happens actually. So this is a theoretical diagram, and that's what the one full circle complete. That's mean 0 to 360-degree complete. Okay, so that's mean there are two stroke happen, one the compression and the power. So right now we're gonna discuss the three stages of combustion with this diagram. So I need to change the position. Okay, so as you can see here, don't get puzzled please, because it's super easy, and you got a spark here also. Okay. So as to describe this diagram, we need to consider it again, and the vertical axis represent the pressure inside the cylinder, and the horizontal axis describes the movement of the pistons, or you can say the crank angle actually, the angle that the crank actually rotates or take place. Whatever, we're gonna see that the ignition leg over here. What is ignition leg actually? As you see that this is starting from 80, 60, 40, 20, but the stroke doesn't start from here. You can see that this in the diagram it has already some pressure, so it has crossed 0 degree. So you can see that from 80 degree on, okay, from descending order, from 80 degree on, it's got a pressure here, it's up to here. I don't know the measurement here, the scale, because I didn't just scale it up. Okay, whatever, it's not important right now. So the compression is taking place, and the piston is going up and up and up and up, and the pressure is increasing, and this point, the spark plug spark and ignite. Yes, in this point, in the point A that I denoted here, the spark take places in spark plug. And what happened actually here? The nucleus flame is what the main flame that takes place, the first flame that takes place and occurs by spark plug, start from here, and the flame got wider and wider. It ignite itself, and then it propagate, and actually when it started, actually I need to draw here. Think that this is combustion chamber over here. Okay, I need to draw here. Okay, so the spark plug have fired something, or spark takeoff occurs. So the first flame will come up from here, and it will ignite the surrounding particles or molecules of UFL mixture of HCO2, whatever it is, hydrocarbons and oxygen. So it will burn and burn and burn and burn, and then the self-propagation start, and it will start from A to B till B. Okay, till B, you see that the ignition started, but the combustion hasn't started yet, because the nucleus flame has to spray, as Mr. Richard said to us. So the flame sprayed and sprayed, and gets self-propagation, and until it reached to the point B, the combustion take place actually. So, okay, listen carefully. The ignition start from here, but the nucleus flame actually ignite, and then it start to ignite the surrounding molecules inside the cylinder, and actually from A to B here, as well as the piston is going up, and also the pressure is increasing, but the pressure suddenly increasing in this alongside. So you can have a quite misunderstanding with this curve and with this curve. This curve is not representing you the pressure here. From here to here, it's not actually representing you the pressure. Actually, it's representing you, or it's denoting you the movement of the piston. Because the pressure is going to take place from here, as you see that the pressure suddenly increases so much, as because the spark take place, the pressure actually started to increase here, and from point B here, the combustion actually take place. Okay, the whole trapped air-fuel mixture got fire in this point totally, and From A to B, we say that ignition lag. Why we say that? Because the moment that in the point A, the spark take occurs, the spark had a lot of heating energy, or the value of heating energy was at its peak point. As the spark take place, or as the spark actually uh, take place from all along from A to B, it actually loses its heating value, or its heating energy, because the first flame that take occurs, or the first molecules or some of molecules that actually it was actually self-propagating, it was actually losing um, that amount of heating value, as because the surrounding molecules were not heated. The surrounding molecule were taking the temperature from that, or taking the heat from that nucleus flame. So that way, as long as it is going it's straight hard here, making an angle, it is actually losing the heating value. And up to this point, it actually, what is with that thing, the potential pressure and the temperature, all is just got lost from here to here. The losses, actually the thermal losses, as we can say that in some point. So it is denoted as a degree theta 1. So this is called ignition lag, actually. From A to B, the trouble, actually, the phenomenon is called ignition lag, and it is represented as theta 1 here. I'm sorry, is represented theta 1. Okay, and right now the second stage, we start from B to C. That's why I told you not to believe in this one, because this, yeah, it's not like that. It's not practical one, it's a theoretical one. So that's why it's very important here, because this is denoting the practical. As you see, the B to C is straight here, and the volume is actually constant. But here, as you see that the combustion take place before the piston reaches to TDC, or some of degree, it's kind of like 20 or something degree before or advance it has take place, and the spark started. And from B to C, from B to here, that intersect this line to this straight line is called TDC. That's mean the piston actually is moving. It's not resting at a point for some time, actually, because we have seen that the piston in theoretical diagram here, that the piston is taking rest here, or and that's why the volume is constant here. But in here, this diagram, you can see that the piston is going up and up and up and up. This is the movement of piston here. It is intersecting here. Sorry, it's not this one. It is intersecting here, and it is also moving up. That's mean the piston has reaches to TDC, and then its father is coming down towards BDC, actually. Okay, now the second stage, as we have said, the self-propagation, is that when the combustion actually takes place there, then the nucleus flame, what I have said, actually, the nucleus flame that actually started the taken heating value from spark plug spark, actually, that now that sprayed that flame in all over the combustion chamber. And this is the stage here up to the peak point of the pressure. Okay, so from B to C, actually, the piston moving up and up and up and up, and the piston reached to TDC, and then again the piston is coming down, because from here the power stroke actually occurred, and after, until it's actually it reaches to the point C. Okay, that's why ignition is not always power stroke. Okay, so from here to here, after the ignition lag, the self-propagation starts from point B, and it is just creating a vibe inside a cylinder, and it is taking place all of it is the combustion chamber inside a cylinder. And after it is reaching to point C, this is the peak pressure. This is the peak pressure that a piston get, actually, because the ignition can be happen from here, combustion can take place here, but the explosion is from right here, actually, after this piston has already visited TDC and is going down to BDC. After some of 15 or 10 degrees here over here, I don't know actually, it got the peak pressure because the explosion took place within a very short time. And from point C, you see that the curve is, you know, downward here up to D, as because this is the power stroke. Okay, so the last one, what it is actually C to D, is called the afterburning. So afterburning is what? From here to here, if your air-fuel ratio is good enough, then your complete combustion is gonna here, and it will produce some of this compound here. But if there's some rich mixture here, like if your air-fuel ratio denoting from this point to here, this is a practical limit, okay? If your air-fuel ratio is below of this thing or before this scale, 14.5 or less 14.5, it is called a rich mixture because the amount of air is less, but the amount of fuel is as the proportion of the air-fuel ratio, it is lower. So that's why it will create a rich mixture. And for that thing in rich mixture, as for the deficiency or the lack of oxygen, amount of oxygen, you're gonna have some of fuel that is going to actually burn after this point actually. So that also burn in this point, and if it's very rich, then it will, you know, emit some of hydrocarbons. Okay, that's what is very odorous. So from C to D, it's called the afterburning position here, and the power stroke actually complete. So that's what the combustion process that take place inside a cylinder, and it's very important to understand these things, because without this one you actually cannot understand the phenomena that take place inside a cylinder. As an engineer, it's very important to understand this. So the video has extended us for a long time, and thank you for watching this, because this video is very long, and I hope that some of boring person like me who really actually got a freakness in studying theory things and theory stuffs can actually enjoy this video. So please subscribe and hit the bell icon to get always tuned with some of very like some of Mr. Richard, the father of engine research. Okay, like some person like them, and I welcome you everyone to watch this video and to share with your friends who actually who have some freakness like us. So thank you very much, and stay tuned with us up to the next video. Please stay safe, stay home. Thank you.